So going into chapter 4, we've taken a couple weeks off, so hopefully some of the information has still been retained. These notes are actually not entirely mine. They're borrowed from another group. So there's another group that's kind of going along with the book in parallel. And so a couple weeks ago, I shared my notes with them, and now they're sharing their notes with us. And so I looked at their notes and I said, these are good enough. I don't need to completely redo these from scratch. So I've made tiny little alterations, but for the most part, it's just shared notes at this point. So just in case things look different from previous weeks, that's why. So looking at the gist of this chapter, we're looking at encoding and evolution. And so we're looking at the various different ways that you can encode data and then pass it through various different communication mediums. So the big questions that we're trying to ask: how do you handle schema changes? How does that change with forward and backward compatibility? So you might update your app, you might update your server, you might do something else, and you need to make sure that across different versions it still is able to communicate and function appropriately and how you expect. And so we're looking at the encoding formats, but we're also looking at some of the different storage and communication formats. So web services, REST, RPC, message passing, etc. And so as we're looking at these different concepts, there's a few different things that we probably want to keep in mind. And the one that I've sort of touched on a little bit is when you need to do updates, there's various different things that can happen. So you can have server-side updates and client-side updates, and you need to make sure that they communicate correctly. And so when I was looking at these notes, it was kind of reminding me of when we were doing Zoom and we would have certain features and we go, oh, you can't do breakout rooms because you don't have this update, or you can't do polls because you don't have this update, or you have a newer version so you can do this, but this other person can't. And so that's kind of similar to these concepts here, a little bit removed, but similar idea where sometimes, like on the client side updates, you're at the mercy of the user. You need to actually make them update in order for a new UI or something to pop up. But you might be able to do a server-side update that just releases an updated view of the data or something like that. So that's something that's important throughout this entire chapter, is understanding how these different encodings and communication mediums might affect your ability to update and be backward and forward compatible. And so the way they split the two different types of data in the book, you have your in-memory data, which is your stuff like your objects, structs, lists, arrays, hash tables, a whole bunch of different stuff, all of the stuff that's optimized to be on your CPU in memory and interacted with directly with the programming language. And then they have the other set, which is what's sent over the network or stored on a disk. And so that's the stuff that's encoded directly with bytes. And so they kind of touch on why do we need to do this translation and what is it useful for? Why don't we just directly dump the memory or do something else? And so the first question is, how do we translate between in-memory data and data that needs to be sent over the network? And that process is called encoding, sometimes serialization, sometimes marshalling, and then the opposite step is called decoding or deserialization or unmarshalling. And so what is the main problem with not just using your programming language's direct encoding? And one of the first ones is that then you're tied specifically to that programming language. So if you pickle something in Python, you're not going to be able to pick it back up in Java, most likely. There might be some magic way to do that, but it's definitely not going to be as easy as some other native form that can be passed between programming languages. And then the other thing is there's also the potential security risks. So if you have some memory structure that you write down and then you expect someone else to pick it up, and then that might have the possibility of running some arbitrary code, then you might run into issues there. And then there's lots of issues with backward and forward compatibility. So if this person's running Python 3 and you're running Python 2, or they have this version of a library that interacts with the data that you are uploading and they have a different version, then you might have issues with that. So you need to be a bit careful with that. And then the other thing is they might be inefficient. So it might take a lot of space, or it might be slow to load or to write. There's all kinds of different things there. Most of the time, their implementations are just focused on getting the data down and making sure it can be reread properly. So looking at the alternatives, the sort of agnostic formats, you can look at JSON, XML, and CSV. Those are probably formats that all of you have been exposed to at least a little bit. They're fairly widely known, but they also have various different challenges associated with them. So XML and CSV, you don't really have a way to distinguish between strings and numbers. So if you have 34 just randomly written in your file, they don't know if that's the string 34 or the number 34. And then there's also issues in JSON with number parsing. So if you have a really large number, then it's not sure exactly what the data type is potentially, and it might get truncated or it might have some other issues there. And so they use this example where Twitter using JavaScript and JSON, they have to keep basically two different versions in order to represent their ID number. And then another great shortcoming is the JSON and XML don't support binary data. And so if you want to encode an image or something else, I've seen those passed in through there, and it becomes a massive bear because it doesn't natively work like that. And then the other challenge with XML and JSON is the complexity of the schema. So you ever look at an XML or a JSON file, you typically have to open it up with a specific program that will help prettify it for you, because it's usually pretty difficult to read because their layouts are fairly complicated. And then looking at CSV, you have no schema. It's just basically rows and rows of data, and you can have all kinds of issues there. And so there's also differences between implementations. So Pandas might open it one way and Excel might open it a different way. And then data table or some other format might do something slightly differently. So there's lots of different struggles with those. They're very common formats. They can be useful, but if you are expecting consistency and good compatibility with different things, then you might have difficulties there. Any questions before going to binary encoding, or any notes?
Yes, I have a question. I know that serialization is usually used in Python, but I've never met marshalling before. What language did this? Do you know?
I'm not entirely sure. The way they kind of posted in the book made it sound like it's just a different word for a similar concept. I know that when I've seen people do stuff with protobufs, like in TensorFlow, they've called it marshalling, and then there's some special process to pass it to TPUs and stuff after it's been marshaled. I don't know the full details of that though.
Yeah, that's right. Marshalling is a general term. It's not a language or application specific term. So you might see it used. I think I've seen it used in like Spark literature, where if you were taking data from various nodes in a cluster and bringing it all back, you know, to the host, then you're sort of marshalling, you're serializing all that. The other thing is there was a note in the book. They said that they're avoiding using the word serialization because they use it later in the book when they're talking about transactions and sequencing events. But I do think serialization is the most common word when people are talking about taking an object and writing it out to a stream or a file.
Mm-hmm.
Which format is recommended?
It just depends on exactly what your use case is. I think that there's not a clear and dry, this is the best format for everything. I think it kind of just depends on exactly what your requirements are. And sometimes it just ultimately doesn't matter. You can have a CSV or you can have an XML file or JSON file. And if it's small, and if you have some way to read it and to write it, then it doesn't really matter. It's not something that's going to have huge performance impacts or add complexity to your code. So moving on to binary encoding. So once you get to larger and larger data, the efficiency and the compactness of your representation ends up becoming more and more important. Because whereas if you have some small company's data and they have a CSV that has 100,000 rows, that's not very big of a deal. But if you can make that 80% smaller, it's the difference between 1 gig versus 200 megabytes. That doesn't really matter. You can still transfer that almost instantly anywhere. But if you go to an even larger company and you say, okay, now this is the difference between a terabyte and 200 gigs or 20 gigs or whatever, that can actually be a very significant savings potentially. So then the efficiency of it actually becomes much more important. And so one of the things that you're talking about, JSON, less verbose than XML, but takes a lot of space compared to the binary formats. And they mentioned there are actually binary encoding options for XML and JSON, but they become a bit complex and they aren't as compact as they could be. So they mentioned message pack that can cut down the size, but then it becomes no longer human readable. And then they kind of propose 3 different alternatives. So there's Thrift and Protos and Avro. And that's kind of the primary bit of this chapter is looking at these formats in more depth. So looking at Apache Thrift, they have 2 different formats. There's binary protocol and compact protocol. And one of the things within Apache Thrift is they have field tags. And so that's sort of like in one of the previous chapters, we were talking about database. I think they were called labels. I'm not sure if I'm mixing that up. But basically, you have a number that maps to a specific concept rather than specific writing it out in its entirety. So you just say this is row 1, but you know that row 1 or column 1 rather equals user ID and column 2 equals some other field. And so you just write 1, 2, 3, 4, 5 rather than actually the full string, and that helps with a little bit of compactness. And then they also, the compact protocol, they didn't go into too much detail, but they just basically said it has various different additional strategies in order to make it even more compact than the binary protocol version. Then they started talking about the protocol buffers, and they say it's similar to the Thrift's compact protocol, and talking about its backward compatibility. You can't change a field tag because it would make all of the previous stuff invalid. And so the tag is heavily used in the byte sequence. Each new field needs a new tag number. New fields cannot be required since new code cannot read data encoded by old code. And so that's kind of the important bit of this chapter is understanding which pieces are forward compatible and which parts are backward compatible. Can we add new fields? Can we remove fields? Can we make our application code ignore this new thing? Or can we make the various different versions match in various different ways? And so that's on the backward compatibility side, but on the forward compatibility, we have the benefit of old code can ignore new tag numbers. So now we have this new field, but our old code can basically just say, I don't know how to do anything with this, so just ignore it, basically. one of the things they mentioned is like with most things, you can make an optional field, but then you can also convert an optional field to become repeated, and then it's handled in this kind of interesting way where it's going to keep a list of these values, and the old code is going to read the newest data. I'm not sure if I'm saying that right. Basically, the compatibility between the two. The new code with the old data sees a list with 0 or 1 elements, and the old code for the new data sees the last element of this. And then moving on to Apache Avro. I'm not sure if I'm saying that right. I've never heard someone say it out loud. That's how I was saying it in my head. But binary encoding format that's slightly different from Protos and Thrift. And it has two different schema languages. One of them is for human editing, and one of them is machine readable. And one of its differences from the others is that it doesn't have tag numbers, but somehow it's still compact. And so the way that it does this is it's encoded as just a list of values. And then the problem is then you need to keep track of the data types and also the schema, essentially. And so in order to do that, you keep a copy of the schema. And the schema is used to tell what data type to look at, and variable length data is supported. And so in coding, you have the writer schema, and it's the schema that's used at write time. And then when it's read, you have the reader schema, and those two can actually be decoupled in some way. They don't have to completely match. One can be translated into the other. And the schema is what the application code is relying on, and it's something that you have to actually generate potentially. And so, like I was mentioning, they don't have to necessarily be the same thing. They just have to be compatible, and then the differences can actually be resolved. They showed a diagram in the book where they said, okay, now the user ID is in a different position than before, and this other field is in a different position, and you just have to make sure that your writer schema and your reader schema have been properly translated, and then the reader schema knows, okay, now this is over here and that's over there, and this is a different ordering slightly. And then to maintain compatibility, fields can only be added or removed if there's a default value. So you have to make sure that there's something to fill in there. And so your reader schema potentially will have to also have that knowledge of what do I want the default value to be in order to add an optional field like that. They mentioned there's backward compatibility limitations, but they didn't really touch on it too much. I don't fully understand the breadth of that. And then they're asking, how does the reader know what the writer's schema was? And there's various different ways that that can be handled. So one of them might be that you just have it at the top of the file and then it's applied for the rest of the file. That's one potential way to do that, but then there's also the complication of what if you have multiple things writing to the same file and you don't know what this specific schema was used for that record. And so there's also the method of keeping a version number associated with each record. So you say, this was written with record 1, this was written with writer schema 1, writer schema 2, writer schema 3, and then it goes and it looks it up and it says, okay, that means that this record needs to be read in this specific way. And then in that way, you can keep a single serialized format that also captures various different versions have been writing to the same thing. And then we know how to read them back out, even though they've actually been written in slightly different formats. And then the other method that they were talking about is you might have a specific, a networked call that you just basically say, okay, send the schema and then read the rest of this in that specific format that you were told to. One of the things they were saying that this Avro format is good for is if you want to dump a database then it's a good format for that. I'm not sure I entirely understand the logic why that's a good format to do that. But if anyone wants to chime in, open to hear more detail about that.
Avro is at the heart of Hadoop. That's where it came out of, if I remember correctly.
But it's the strong schema relationship that you have to have with it. Most databases are written in some kind of binary format, and you need the schema to decode that. It translates directly over into Avro.
Mm-hmm. Okay.
Yeah, so I think the idea is that generally speaking, your databases are large, so the amount of space that you consume by adding schema is you know, it's a drop in the bucket. So by doing it this way, you basically have self-describing files.
Mm-hmm.
And so then rather than having some other convention that people need to understand, you just like, oh, here's a table. I don't really care what the columns are. If I dump it out, it'll be self-describing.
Mm-hmm.
Like a SQL dump.
And so one of the things they were mentioning is it also allows for optional code generation. I can vaguely see how this is useful, but I've always played in Python land, so I also don't know the full depths of this, why exactly you would need all of the types specifically defined. Yeah, and so like you guys were mentioning, self-describing, it comes along with all of that information because you're keeping track of the schema potentially.
Yeah, so Ryan, like I haven't programmed with this, but hypothetically, if you have an Avro, I'll call it engine for C++, right? Then basically when you get a file, you don't have to then write the import routine for it. Avro can simply take the schema and write the code necessary to import it.
Mm-hmm.
So that's sort of the
yeah.
I forget what wording they use, but the auto code generation part of it.
Yeah. Okay.
So like I know people in my office, we get text files from our clients, and people are writing these packages to import them. Column 1 is first name, column 2 is last name, column 3,
Yeah.
And you don't have to do that if you have a format like that.
Mm-hmm.
I have a question. Is that similar to protocol buffers generated code?
Yeah, they're both basically, since they're doing the on disk, we'll say on disk file format to a language specific representation, you get the same kind of generated code to do that. I'm going to read from disk and I'll just give you a object or a data structure that is what you're looking for. So you see it on there, you see protobufs. You can extend it to the RPC stuff like gRPC. They have a lot of code generation that for the same reasons.
So I have a lot of experience using protocol buffer, and it happens like you have the proto, and then you have the protocol buffer file to have all the schema, the fields, and then you use the protocol compiler to compile the schema, the proto schema. Then you can specify what language you want. For example, I want Java, and then it after you run the command, it will auto generate a Java file which contains the schema. So it can easily do something like the get method, set method are all there defined. So if you want to deal with the you want to write any code related to it, so you can just directly use it.
Yeah, they did a lot of effort in these to make them cross language, cross platform compatible, because the format is going to be the format regardless, but getting it to and from whatever language or environment you're running in is the thing that kind of like that's what makes it programmer friendly, user friendly. Yeah.
Yeah, that sounds really cool. The idea that, you know, if you know what the schema of the file is, then it'll create all the necessary struct in your language to load that in. And then from there, if you want to do something application specific, it's up to you. You know, if you're sorting it, putting it in a tree, whatever, that's up to you. But at least just the importing, you don't have to sit there and write boilerplate code.
So I guess one of my questions is they mentioned here the possibility of having different versions of the schema for different records. I wonder how that interacts with taking a full database dump, essentially, when you're interacting multiple different schemas. I'm curious how that would look like.
I think it's one of those things where it's you can do it with multiple schemas. So if you think about like spreading stuff across a large, large set of data, right? And you're going to be adding to that data over time. Then at some point you might realize you need additional fields. You need to change fields or something. And so like the files you write later are the ones that get the newer version. Mm-hmm. And you could do that kind of mid-file depending on what you actually want to make the file itself look like versus just the encoding that goes into the file, if that makes sense. Mm-hmm. So I think it's kind of like if you were to do a dump of an entire database and write it out once, you're going to write it with the same format. Mm-hmm. If you're going to be dumping that database once a day and then doing incremental write-outs, that's where you'll start to see this mix of version formats.
Yeah.
I have a question. I don't see Parquet here. Is it kind of Aura, just with more structure?
They did have one mention of Parquet in the book, and they were saying that maybe during this export step, it might be a good idea to do a rewrite as Parquet. And they said specifically, since it's column based, then they can do the various different analytic processes on it. But that was all that they mentioned of that in the book.
Yeah, I want to say this one is definitely, it seems more focused on online transactional kind of items. Because the formats that are chosen are usually row-based ones, not necessarily a true, it says data intensive versus big data, where you'll see a lot more of the column formats in the big data stuff, in the analytics kind of projects. So it's just, it's interesting that it is glossed over here, because I mean, Parquet is kind of what I see all the time with any of our analytics stuff.
Maybe if the book were newer, there would have been more mention of Parquet. But yeah, I get the same sense, Chris, that the focus is on if you are actually shipping data between a client and a server, and it might not be like client server like browser and web server, but more like
streaming engines, queues, anything that you're shipping.
Yeah, like a hospital and a doctor's office, or an auto parts supplier and a car manufacturer, right? And so you're establishing some kind of application, and they're moving data, and you expect that over time you're going to have version upgrades. You're going to have to deal with forward compatibility, backward compatibility. Maybe as an auto manufacturer, you might have 700 suppliers, and they're not all going to upgrade their clients when you upgrade your server. I think that's more the use case.
Yeah, that's a great example.
By the way, when I was reading the Google Cloud documentation, I do see a doc talking about exporting database from Cloud Spanner to Avro. Avro is the format we're just talking about. Initially, I'm just like, 2 days ago when I read it, I was just curious why they trying to export to Avro format.
Well, I mean, Avro is going to be sort of product platform independent. So that's good news. So that if you're exporting it from there and pulling it into something completely different, you don't know if they're pulling it into, you know, AWS, if they're pulling it into SQL or Oracle or whatever. So then at least it's, you know, not vendor specific.
I see, because it's self-describing with the schema inside.
Yeah, exactly. And so then you could be, you know, moving it anywhere in theory.
I also think of, like, if you're doing an analytics piece, you usually want to, you know, take a look at all of the data, not just a subset of it. If you're directly interacting with a database, you're constantly putting load on that database. You're constantly kind of adding a whole lot to it. It's not nearly as efficient as, like, if you just had raw data files and you were just like, okay, I'm going to load these up how I load them. So, you know, that step one is dump the data from the database, and then step two is load it into the things that you're going to be reading and rereading continuously. So it like reading from Avro is a lot faster than trying to dump a database, right? Because you're already done that database dump once, kind of thing.
But I have another question. I think Avro, the format still kind of role-based from the storage format perspective, right? I think for analytical purpose, it's more preferred to use column-based storage format. Like
that is
Apache, Parquet.
like Parquet.
ARQE, yeah, Parquet, yeah.
It might help to understand where it came from. 2005, I was working for a search engine company, and at the heart of the search engine was a white paper that was produced by Google, and it outlined this storage framework. It was designed to ingest content from the internet on all forms, be able to identify every object that was being laid out on disk, and with the intent that it would be a permanent storage. So the schema is carried through, and year over year, you're going to get new data formats, and new content, and you needed the schema to change accordingly. And that's one of the reasons why this is at the heart of Hadoop, because at the heart of Hadoop is that technology for searching the internet. And that's where the roots for it come from. So Avro is pretty powerful in that it is a common format that can be moved between a number of different systems and platforms, but it should not be the end all unless you are doing Hadoop type searches. If you're doing that kind of, then it's absolutely perfect for that. But as we all know, every data has a certain algorithm that applies to it best, which means different indexing, different technologies, whether it's big data or it's image data, or whether it's columnar data or database. There's a reason why we have so many different formats, is that it aligns to the data. It doesn't necessarily align to human readable form.
Yeah, I want to echo the workload that you're looking for really has a huge impact on what your data structure, the efficiency you want with your data structure. If you're just looking for, the simple example is if you gotta look at if you were trying to evaluate every single entry inside your database, the row format makes sense. But if it is what you're evaluating is a row at a time, right? But if you're just looking for a subset of columns, then a column, interface makes a lot more sense, right? So in some ways, it's what is the question you want to ask, and that will have an impact on what you need to structure your data as. If you don't know what that is a priori, you kind of pick one based on your guess and you go with that.
So summarizing that section, the key takeaways: binary encodings are more compact. The schema gives you the documentation that we've kind of been discussing for a bit now. Keeping a database of schemas allows for checking backward and forward compatibility. And then code generation is useful for type checking and compile time.
I have another quick question. So do we have an idea, like for those binary formats we're just talking about, how they are adopted in those big companies?
I don't really have much background on that. It seems like since they are designed by some of the big companies they mentioned, Facebook and Google and various companies are behind them, I would assume that they're used quite heavily by them, but I can't necessarily speak on that.
I want to say you see from like the open source and the analytics tools, there's a lot of support for multiple formats. And so adoption there tends to be a little bit wider. For something like, I'll be honest, protobuf I'm used to seeing as part of a network transport rather than as a storage format. So that one that one came out of Google and has a lot more usage there, but I know, I've seen protobuf in other companies quite a bit when doing network communications.
So the next section of the book, now that they've talked about encoding, is they're talking about how do you actually kind of send this information around in various different formats. So they're asking, how does data flow between processes? One of the options they gave was data flow through databases. In this scenario, backward compatibility is necessary. So they're saying might only be one process writing and reading from the databases. Future versions of that process and database need to read old data too. I guess that's the last bullet point. I'll say that for later. So forward compatibility is also necessary. Many processes will read and write to the database. Some processes may have gotten the latest update and are writing new data to the database with newer code, then older code could read that data. So basically, in that format, you can have a new process that says, I'm going to write a new field, and then an old read process can grab it and say, okay, I don't know what to do with that column, but just read the parts that I need anyways. And vice versa, basically. But one of the problems is you might have new code that writes a new field, and then old code that's supposed to update that record might look at it and say, there's this new column, what do I write here? And so there's various different ways that can be handled, that's some sort of edge case that you need to look into if you're doing some sort of rolling upgrade where you might have to coexist in multiple different versions. And so one of the kind of phrases that I think was important was that data outlives code. So you might fill a database with a whole bunch of data and it's going to exist for a very long time. We're saying, let's say it exists for 5+ years and you have a very, very old version that was written, and then it changes and changes and changes and changes. And over time, you have to make sure that it's still potentially able to look at that record and read it in properly or update it or do various different steps on top of it. So you have to also keep that in mind the initial time that you're writing data. You have to know that there's probably going to be changes in the future. So you have to look at that a little bit and make sure you plan for that. And then the other,
I'll just echo. I'll just echo that, Ryan. So like, for example, I've worked for, mostly small to mid-sized companies. And so say, for example, we add a new required field to the user table and it's birth date, right? It's pretty easy for us to basically like shut down the system, update the schema, update the code, and then say, voila, now version 2 is out and every reader knows that birth date's a field and every writer knows that it's a required field. But if you're Twitter and you suddenly add a new field to the user table called, opt-in number 17, security preference opt-in number 17, yes, no. you can't just shut down all of Twitter and update every system to know this. So you're going to have these forward backward compatibility. It doesn't matter whether you're using a relational or a non-relational, like the stuff we talked about before the break, different kinds of stores. Ultimately, you have your user ID, that's your key. And so you could be, storing this in some NoSQL format, but ultimately, whatever that record is that you yank back with that user ID key, you're going to now have these forward backward compatibility issues. So that's something that I don't think I really appreciated the depth of how much that's a problem until reading this book.
Yeah. So the second one that they were talking about, data flowing through services. So you might have the REST API or RPC. I believe that this was remote procedure call. So a key design goal of a service-oriented architecture is to make the application easier to change and maintain by making services independently deployable and evolvable. So at least when I think of REST APIs, you think of, well, there might be different versions of the REST API. And so you might be able to say, okay, this person is interacting with this specific API and this other person on the old version is looking at a different version of the API. And so you can just directly expose different formats and then kind of hide away some of that complexity. So if you're interacting between either internal to your company or different organizations, you might be able to allow that to operate in a way that other people can continue interacting in the way that you expected, but also add some new features and stuff like that for people who want whatever new information you started storing, potentially. Below that, this means that there could be old and new versions of servers running at the same time, often across many teams. Data encapsulated across clients and servers must be compatible across these versions. So like I was saying, you have different versions and you might have to make sure that they're either intercompatible or people are interacting with the correct versions potentially. They mentioned SOAP, but they didn't really say a whole lot about it. They say that it's kind of fallen out of favor and smaller companies might add additional complexity and interoperability challenges. And then they talked about the RPC model, and they're saying that it's basically like calling a function, but from some remote network service. And then they were saying that there's various different challenges that go along with this. So when you call a function in your programming language, you expect that to return something. And if it doesn't return something, then some error happened. But it's also possible in RPCs that it was just some network issue where it's like, okay, well, you lost connectivity, so you didn't actually send the request, or they lost connectivity, so they didn't actually send the response. So there's various different issues that can happen. They're unrelated to the code, and then you have to build around that possibility, saying it might actually happen, but it didn't communicate properly. So one of the things they were talking about is you might send the request and then you don't get a response back, but it actually did it. And so your code says, well, it looks like I didn't get a response, so I'm going to send the request again. And then all of a sudden you've accidentally done the same action twice, or you've written two records, or you've caused some other issue there. And then another problem is it has higher latency. So if you're doing something locally, obviously it happens almost instantaneously. But if you're sending it across the world, then you might have a longer wait time potentially. And so that works decently if you're sending something small, but if you're sending something much bigger, it might slow things down, or it might not even be feasible. And so you might have to do something with pointers, or one of the ways that I had done stuff in the past was we made this API that was doing these this search process on some documents. And so it was a bunch of PDFs, and it could be hundreds of pages. And so we had to make a separate upload step versus a processing step. And then the processing step, all that it did was point to the location of the document. So you didn't have to send over this 300-page document every time you wanted to do analysis. And it made it much easier in terms of the API calls. Then they also talked about challenges with data type compatibility across languages. And so that's just inherent in RPCs. And then they talked a tiny bit about streams. And so they're basically saying it's just a series of requests and responses rather than just one. So you're doing that over and over again. And then they talked a little bit about promises. I don't fully understand the scope of that. They didn't explain it in too much detail, but it seemed to be that it's just the process of expecting that something might fail. And then they're saying RPC protocols with binary encoding have better performance than generic JSON over REST. So that kind of goes along with what we talked about before. The binary encoding is more compact, and then the JSON might be slightly larger, so you get better performance out of it. But the RESTful APIs have a lot of nice things about them because you can use various tools in order to document them better, and it makes experimentation and debugging easier. I've seen just a whole lot of people using Swagger and various other tools to interact with that. So they mentioned RPCs, mostly used for in your own organization, and then REST probably more often something that you might expose to the public. Backward and forward compatibility properties come from the encoding format that you use. So if you have any number of different encodings, then you're going to have similar properties as whatever encoding you're using. And then you also have the same challenges with versioning and forward and backward compatibility. And then getting through the third method that they talk about through message passing. In this way, my understanding of it at least was sort of the message broker is kind of an intermediate step that it might take where you send a message to this broker and then the other person can potentially pick it up, or it's just essentially left there in the queue. And then people can just send messages all at the same time. You're not necessarily sending a request and then waiting for a response. And that can reduce some of the issues there. You don't have as much idleness potentially because everything's working asynchronously. And so the problems that this kind of solves is they're saying the recipient might be overloaded and this acts as sort of a buffer. So if you're making a request to some service and right now they have too much going on, then it might just be rejected. And in this paradigm, you send it to the message broker and then the other thing can come in and give a response when it's actually available rather than just giving you a time limit. And so they're saying this prevents messages from being lost, can redeliver messages potentially if something goes awry. And then it also protects the IP address. So you don't necessarily have to know this specific machine is going to give me my response. You just say, basically put this to the message broker and then any system can respond to it. And they were saying that that's kind of nice because if you're using AWS or some other cloud infrastructure, you might have instances that are changing IP addresses all the time and spinning up, spinning down, doing various different things. And then they're also saying that this, the message broker can kind of function to broadcast out to many different targets rather than just a single one. And that can also offer some efficiency gains. Sort of saying the intermediary is not a network connection, it just temporarily stores the message and then allows it to be available. So I think the way they described it is sort of like a mailbox where you can put something there and then someone else can pick it up when they want. sender doesn't wait for the message to be delivered. Consumers of a topic might even process the message and then queue another topic, or could enqueue to a response queue so that the original sender gets a reply. So one of the things that I think was important that they mentioned here is you don't actually necessarily have to go to a specific message broker, read some request or something, and then return back information to exactly the same message broker. You can send it to any number of different ones, and then it can also be picked up again somewhere else. And that kind of makes it so that it's more scattered, but it allows more immediacy potentially, without having synchronous requirements. Then they're saying you can use any encoding format. I think that's probably dependent on what exactly you're using, but I think that that's probably a good general process to have. And then they talked about the distributed actor frameworks. This one didn't entirely connect for me, and for their notes, I don't think it entirely connected either. I don't know if anyone can talk to that.
You want to talk,
So-
I mean, in regards to message brokering and IoT? 'Cause that's, I've been doing an extensive amount of that using MQTT and IoT devices.
Or you were talking more about the actor model, right?
Yeah, the distributed actor frameworks. It was kind of just an afterthought in the chapter. It was one of the last things they mentioned, but it only got a paragraph really.
Yeah, I mean, it's the idea of you try to take what your business logic or your specific function details are down to the smallest unit that you can, and then you could send it to any of the anyone who is capable of doing that type of function. So you basically spin up a whole bunch of workers that are capable of performing that function. And those are what you refer to as your actors, and actors strictly communicate by message passing. So that's why it's relevant to this particular section. It is kind of like throwing on this giant concept at the tail end of something, which is kind of funny, but that really is, it's just taking a lot of what was described here and formalizing it.
Oh, interesting.
Thanks, Chris. So I think because of the timing of when this book came out, right? I don't think the author really emphasized. Today, I would say these large scalable applications, they're all using things like Kafka, for super large scale applications. I think the message passing architecture has proven to be the one that's the most robust and scalable. If you want to emulate synchronous activity, you can, right? Even though it's asynchronous, you can pass the message saying whatever, like, give me the user ID's first name and last name. And then if you want, you can just sit and do nothing until you get a message back. So if you want synchronous, you can always, emulate that. But if you don't, then of course it gives you the flexibility of asynchronous, and it makes explicit that if something fails, if something times out, you have to decide what to do. Instead of before, if you did like RPC, it could time out, but you could, as a naive programmer, just write your code and not catch that scenario, not think about it, just assume it's going to work, and then it works great until all of a sudden, something times out, and then all of a sudden you realize you never planned for that case. And then I'll say, sort of tongue-in-cheek, you can have massively scaled things, and then when your actual message broker crashes, that's when you have the entire AWS East Coast down. Because everybody's depending on this message broker to do anything.
Well, that's, you turn on persistent store, you turn on guaranteed delivery, message delivery. There's other things you can do.
I think one of the big things to highlight here is you are trading a complexity for robustness. Because to like the example earlier, like, oh, if I'm a user and I send a request to the upstream service and it's got to pass through a bunch of message brokers, how do we know that that message should come back to me? Because you get a lot of disconnect. So you have to add and track that. That's just one of the examples of complexity that it kind of introduces. And like the RPC models and everything, it's a little more, you can do a lot of async with that, but they tend, people tend to treat them a little more synchronously. And so the reasoning about it becomes a little bit more straightforward. But there's definitely trade-offs.
Yeah, I think that's a good point, Chris.
Yeah.
So it's probably fair to say that to do the same thing with message passing overall, if you look at the amount of like compute resources consumed by all the different servers, you know what I mean? The requester, the message broker, the recipient, right? It's probably doing more work overall. But the good news is, even though it's doing more total work, if you throw a little bit of hardware at it, it actually will scale better than most of these other architectures, because it can be scaled out horizontally, right?
Sorry, I'm always hesitant about making broad statements like that because there's a lot of things that are really workload specific.
Yeah,
but it does
statelessness.
horizontally scale better. Yeah.
Yeah. Well, you got to ask the question: does the application keep the statefulness at the client, or is it maintain the state within the database, or what is the device that you're communicating with? Got to ask all those questions.
It seems to me like at the minimum, it's going to at least try to minimize the amount of idle time of systems. Whether or not that ends up in better scaling or more efficiency, I'm not sure if that's guaranteed, but I do think that it sounds like it would reduce idle time because you're not waiting for responses and you're moving on to additional work potentially.
Yeah, I don't know. I mean, I'm learning this stuff. I'm definitely not the expert in this kind of stuff, but it seems to me that in this message passing scheme, you can have multiple requesters. You can scale up, the number of servers you have handling the as message brokers. You can scale that horizontally, and then you, depending on the architecture, if you're using things more like RESTful type processes, you can also then scale up the number of people serving whatever. I don't know what the technical term is. Pulling things off of these message queues off the top. So consumers. Thank you, Chris. So it seems to me that there is a reason why, right? These internet giants are using Kafka, Kinesis, whatever, using these message passing architectures for their really large operations.
Yeah, at my company, we use Kafka and for transaction data, and like the message broker, maybe each transaction may have like 2,000 fields, but then for the subscriber, they can say what kind of set of filters for what kind of topic what kind of transactions you're interested in, and also specify in amount all those 2,000 fields, which are maybe I only need 50 fields. So like this message brokers, like Kafka, really helps you to narrow down to a subset of data to receive and do it asynchronously, so you don't have to like every hour run like a hive query to get data that you want. So this way is more flexible and less intensive, I guess.
Yeah, and we have a similar pattern where when a request comes in, like it usually actually comes through a lot of synchronous or RPC-based functions to get a response to the user. But at the same time, when it does the transaction update or it does a particular item, it's like, oh, and at the same time, I'm going to send this event that this business event that the user did this function. That gets put into Kafka. And then our, clickstream analysis and everything kind of pulls off from that. So you'll even see mixture of these architectures based on what the need is. And so we see that even in the same application.
One of the things that I saw drove a lot of the adoption of Kafka when I was working for Centene was the fact that they had so many different systems, right, that had their own databases. And the ability to effectively decouple one system from another, but still be able to pass information between them was really what was driving that sort of message-oriented approach. So that, you had a system that was used for registration, another one for credentialing, another one for reporting, et cetera, et cetera. And even if they necessarily ended up all pulling from the same database effectively, it was just a way of decoupling them so they could make requests and get the information that they particularly wanted.
That's cool. So what both you and Chris are saying is that you could have a new use case and that the person who's producing the data wouldn't even have to know, they wouldn't have to change anything. Basically, you're adding another consumer off of that topic, that queue, but the person who's adding to the queue doesn't even need to know that they went from one consumer to 100.
Yeah,
that's part of
the
it.
thing
Yeah.
that matters is the registration of the target. So when the data comes in, I mean, some of the sensor networks that I've been involved in, we can add a new sensor that's delivering a whole new set of data. The only thing that matters is that initial trigger at the head of the stream, because that's going to route through the message broker to the consumer that's going to consume that data.
Cool.
Does that make sense? Because when you look at the framework, I could have 200 or 300 sensors out there all sending blotches of different types of data. The header is going to direct that message when it comes in. It hits the distribution or basically the front end servers. It's going to see that message handler, and then it's going to route it to the subscribers of that message. And the subscribers of the message are the people that are expecting that data to arrive. And it's one of the technologies I'm working with is actually dealing with cell phones. So the messages will come in, anybody who's subscribed or expecting that data will hit the message broker, reroute, and get replicated out to the cell phones that have registered for that data. So it's a one way of delivering real-time activity right to the devices that are expecting it. So message broker is quite handy.
And it's fair to say, right, John, that if you're creating a workload in terms of figuring out, who all the recipients are that need this, or, here's the 50 out of the 2000 fields or whatever, all this stuff, then that's where I was trying to say, the idea is you can scale out horizontally the number of servers you have processing all this on your message broker system, right?
Yeah, exactly. So I give you an example. I've got one prototype I've got is a pool sensor that it basically collects pressure from the pool, the inbound temperature and outbound temperatures. You can monitor the heating capability and stuff like that, right? That sensor is a little tiny Arduino box that's taking the data, transmitting it to my broker. That broker routes it to whatever monitors I have going. So I got one device collecting the temperature information, another device connecting the pressure sensor to do different notifications. So it's just, you can have fun with it.
So we're over time, technically, we've rearranged things. So this group is supposed to close out at 1:15. So I think I'm going to take a very quick bathroom break, but we'll swap over to project collaboration time if anyone wants to stick on and discuss some things that they're working on or look at Kaggle competitions.
All right, great. Well, thanks, Ryan. Thanks for everyone else who helped with the discussion. And then just for the record, next week I actually have scheduled the book club from 12 to 1:30. So it seems like 1:15 isn't enough based on the last two chapters. So
Sounds good.
So
Thanks,
we'll see if
Good
we
luck,
can keep
everybody.
to 1:30.
Thank you.
Thanks, John.
Thanks, everyone.
Thank you.
See you, everybody.
You're on.
Thanks,